Hi, welcome to Unacademy. Unacademy is the India's largest online learning platform. So I'm welcoming you all to this beautiful online learning platform. Now we are happy to announce that we are going to start the training for GATE and engineering service students. Students who are appearing for GATE and engineering service examinations. We are going to providing the training to them. About myself, I G Venkata. I have 16 plus years of teaching experience. So far, I mentored more than 60,000 students for their GATE examination. At present, I am pursuing PhD from JNTU Kakinada. My specialization is VLSI. Now, see if this Unacademy learning app is in your device, it's okay. Otherwise, just check how to get this Unacademy learning app in your device. Just go to Play Store, type Unacademy in that. After typing Unacademy, just you get the app like this. Go to install button, click it. It will install the Unacademy learning app into your device. Once you open that Unacademy learning app in your device, it will shows you what are the different courses available in Unacademy, and in each course who are the top faculties handling the subjects in each course. You get that information. Okay. Now here you can see few of the top educators in Unacademy. More Tiwari sir, he is the IIT topper. Ankit Goyal sir, he obtained 2 times All India first rank in GATE Electrical, and he is the gold medalist from IIT Indore. And Jain sir, he is the top faculty from CSE department. Jaspal Singh sir, he is the ex IES officer. Okay, his All India rank is 4. And here are few more top educators in different departments. Now we are happy to announce that we started 2 new batches, one for GATE 2022, other one is for GATE 2023. There is a SN batch for GATE 2023. This is for mechanical engineering. This batch started from 8th February 2021. Here are the top faculties who are handling the subjects in this. Next, there is a eval batch for GATE 2022. This is for mechanical engineering, and this batch started from 8th February. Here are the top faculty who are handling the classes in this batch. And again there is a ascend batch for GATE 2023 for civil engineering. Okay, this batch started from 8th February 2021. Here are the top faculty who are handling the classes for civil engineering. And again there is a evolve batch for GATE 2022. This is for civil engineering. So these are the top faculty who are handling the subjects in this, and this batch started from 8th February. Now we are moving to computer science and information technology department. Now there is a evolve batch for GATE 2022 for computer science and information technology. Here are the top faculty who are handling the subjects in this department. Now this batch started from 8th February 2021, and please don't forget to use my code VROW10 during subscription. VROW10 during subscription, don't forget. By using this code during subscription, you get 10% discount. You get 10% discount. Okay, again there is a ascend batch for GATE 2023 for electrical engineering. This batch started from 1st February 2021. And again there is a ascend batch for GATE 2023. This time this is for electronics and communication engineering department. Here are the top faculty who are handling the subjects in this department. So this batch started from 1st February 2021. Again there is a evolve batch for GATE 2022 for electrical engineering. Okay, this batch started from 1st February 2021. Okay, and here are the top faculty who are handling the subjects in this. And again, there is a evolve batch for GATE 2022 Electronics and Communication Engineering. This batch started from 1st February 2021. And don't forget to use my code VRAW10 during subscription to get 10% discount. VRAW10 to get 10% discount. Okay. And there is a chemical engineering department. So this batch started from 25th January. This is a evolve batch for GATE 2022. If any of your friends are from chemical engineering department, please inform this one to them. Okay, because at outside it is very difficult to get the chemical engineering department training for GATE examination. Okay, now once brief just to verify what are the different engineering disciplines available in Unacademy for GATE and service examinations: mechanical engineering, electrical engineering, civil engineering, production and industrial, instrumentation engineering, computer science and IT department, ECE, electronics and communication engineering, and chemical engineering. These are the different engineering departments available in Unacademy. Now, there are two subscriptions. One is plus subscription. This is the basic plan. Other one is iconic plan. This is the next level of the plan. It will take your preparation to the next level. Here we are providing a personal coach to you. With the help of this personal coach, we will take your preparation to the next level. So what is the next level? What it means? You may ask that. I will explain that. First of all, here are the commonalities. Your classes are taken care by the India's best educators, and there are interactive live classes, and structured courses and PDFs are available, and live tests and quizzes. Okay, now here we are going to show the difference. Here we are going to show the difference. Once you written the live tests and quizzes, okay, your answers are going to be analyzed, and from that we will prepare a note. In that note, where you are strong, where you need preparation, where you are doing mistakes. Even though you are preparing everything well, sometimes we are doing little bit mistakes during practice. Okay, so we will identify those gaps, and our personal coach is going to give a solution to that. Okay, this is the personalized test analysis. That's what I explained here. Based on all these things, we prepare a proper study planner to you and a proper study material to you. With the help of these two, student can get success in their examinations. No doubt at all. Okay. So now just we check the cost of each and every subscription. Now plus plan is available at different subscriptions: 1 month subscription, 3 month subscription, 6 month subscription, 1 year subscription, 1.5 year subscription, and 2 year subscription. As a faculty, I recommend to the students to go for minimum 1 year subscription, minimum. Okay, because in this 1 year you can complete all the subjects thoroughly, and you can rewind that multiple times, and you can write multiple examinations. Okay, and you can assess where you are. Okay, and you can identify the gaps, and you can fulfill those gaps by rewinding the subject once again. So for that you need minimum 1 year. Okay, and the cost of this one, if you check, it is only 30,250 rupees. By using my code during subscription, okay, after that it is going to be only 27,225 rupees. And if you compare the cost of this, it is approximately the amount of cost what you are spending for transport if you joined outside for a training. If you are joined somewhere for taking the training offline, so during weekends and public holidays you need to move from your home to the training location. So for that, throughout the year, for transportation itself, more or less cost this much. Okay, so this is just cost of that one. By staying at your home itself, you can get the benefits more than that. Okay, and we move to the iconic plan. Here only two subscriptions, 1 year subscription and 2 year subscriptions. For 1 year subscription, its cost is 50,250 rupees. Okay, and for 2 year subscription, its cost is 74,000. Okay, now by using my code during subscription VRAW10, you can get it by 45,225 rupees only. Here, personal coach is going to be we are providing to you to take your preparation to the next level. That personal coach is going to analyze the things what you are writing in your examinations. Based on that, they will prepare a note and they will recommend you where you are doing mistakes and where you are strong and where you need more preparation. Okay, with that analysis, a student can identify the gaps in their preparation, and by filling that gaps, definitely he get success in their examinations. That is our intention to provide the personal coach. And if you observe the cost of it, this cost is more or less close to the amount what you are paying at outside when you join for training. Okay, by staying at your home itself, you can get the more benefits compared to that. So my dear students, don't waste your time. Whatever the thing is happened. Okay, your learning process cannot be stopped. Without wasting time, enroll as early as possible and get more benefits. Thank you. Now I am moving to our topic. Today's topic is problems on PN-Junction Diode. Already last session we done some problems. Now I am moving to the next problems. Yeah. So this is the problem we solved in previous session. Okay. So this one is completed and this one also completed. Dynamic and forward dynamic and reverse dynamic resistance. Sorry. Now, so the next problem is, see this, at 300 Kelvin, a diode current of 1 milliamp, a certain germanium diode requires a forward bias of 0.1435 volts, whereas a certain silicon diode requires the forward bias of 0.718 volts. Under the conditions stated above, the closest approximation of the ratio of reverse saturation current in germanium diode to that in silicon diode. See this. Under the conditions stated above, the closest approximation of ratio of reverse saturation current in germanium diode to that in silicon diode. That means they want reverse saturation current in germanium by reverse saturation current in silicon. That is the ratio they want. And they given forward bias voltages also. Okay. Now I am going to writing the equation for the diode currents. Now for germanium, so our basic current equation is ID equals to I naught into e power Vd by eta Vt. Vd by eta Vt. Okay. Now for a germanium, I am writing ID. Germanium is given it as 1 milliamp. Okay, and the same value is going to be maintained by the silicon also. whereas certain silicon diode requires the forward bias of this much under the conditions stated above. That means to maintain the same current, it required this much forward voltage. So this is the idea of silicon also. So both the currents are equal. Okay, and I am going to remove the eta value. Let us take eta equals to 1. Now, diode germanium current. Germanium current is I naught of germanium into E power. In case of germanium, the required forward voltage is 0.1435 volts. So 0.1435 divided by Vt. So Vt value is 0.026 volts equals to I naught of silicon into E power. Forward voltage required for silicon is 0.718. 0.718 by 0.026. So we need I naught of germanium by I naught of silicon. Just take this one this side and this one this side. Now it is I naught of germanium by I naught of silicon is I naught of germanium by I naught of silicon is E power 0.718 by 0.026 divided by E power 0.1435 divided by 0.026. Its value is e power 0.718 minus 0.1435 divided by 0.026. Okay, now just I am simplifying this. 0.718 minus 0.1435 divided by 0.026, that is 22.0. So e power 22.0, e power 22.0, that is a 3946.73. So you can take it approximately, it is a 3.9 into 10 power 3. So they given 4 into 10 power 3. This is the approximate value. So approximately 4 into 10 power 3. That is the ratio. Okay. See here, just they given both are same conditions, under same conditions. Both are providing 1 milliamperes of current, but different applied forward voltage. Okay, default we are taking ideality factor 1. If they given a certain data for ideality factor, then you can use it. So this is the problem, and we are moving to the next one. See this problem. Consider the following parameters in silicon PN junction. Na equals to Nd equals to 10 power 16 per centimeter cube, and Ni equals to 1.5 into 10 power 10 per centimeter cube. Diffusion coefficient of electrons 25 centimeter square per second, and diffusion coefficient of holes is 10 centimeter square per second. Hole lifetime and electron lifetime is 5 into 10 power minus 7 seconds, and epsilon r is 11.7. Calculate the reverse saturation current per unit area. So we have an equation for reverse saturation current. I naught is A into Q into Ni square into dP by Lp into 1 by Nd plus dN by Ln into 1 by Na. This is the reverse saturation current equation. So already we derived this equation in class. Previous class we derived all these equations. Okay. So they given d and dp, no problem, tau and tau p, but we need Lp and Ln. Okay, first, and but they want reverse saturation current per unit area. Unit area means just to take this A this side. Therefore, our required data is I naught by A, which is Q into Ni square into D value is L is root to dP into Lp. We know that root to dP into Lp. Okay, sorry, root dP into tau p. By cancelling this one, this with this, now you get here square root of, sorry, you get it as 1 by Nd into square root of dP by tau p plus 1 by Na times square root of dN by tau n. This is the data. Okay, so they given everything to you, just substitute the values in that. Q, we know that 1.6 into 10 power minus 19 into Ni square, 1.5 into 10 power 10 Ni value, 1.5 into 10 power 10 into 1.5 into 10 power 10 into 1 by Nd. So Na equals to Nd. So once Na equals to Nd, you can take common that value. So it is a 10 power 16 into square root of dP by tau p. dP is 10, tau p is 5 into 10 power minus 7. 5 into 10 power minus 7 plus 1 by 10 power 16 into square root of dN by tau n. dN is 25, tau n is 5 into 10 power minus 7. Just simplify this. Okay, now it is see this is 10 power 20, this is 19, this is 10 power 20. Now we can write it as 16. So 16 into 1.5 into 1.5, 2.25, 2.25 into 10 power 16, I am taking common, 1 by 10 power 16 I am taking common, into square root of 10 by 5 into 10 power minus 7. Okay, so you can write it as a 0.5 into 10 power minus 6, and 0.5, 10 by 0.5 is 20, root 20 by, so it is 10 power minus 3 into square root of 20 here. Similarly, it is 0.5, it is a square root of 50 by 10 power minus 3. Now just simplify this. 16 into 2.25, that is 36. 36 by taking 10 power minus 3 common, and it is 10 power 16, so it is 10 power 13 into root 20 plus root 50, square root of 20, it is 4.47, and root 50, square root of 50, it is 7.07. just add these two plus 4.47, that is 11.54 into 36. into 36. That is 415.478 into 10 power minus 13 amperes. Just we check, are they given any way units to this? They did not give any. They did not give in any unit. Okay. Now you can write simply like that. Okay. This is the amount of reverse saturation current. So this is your complete problem. Okay, sir. Yeah. Next, we are moving to next problem. Now, the static characteristics of an adequately forward biased PN junction is a straight line. See, static characteristics of an adequately forward biased PN junction is a straight line if plot is off. See, generally we know the equation plot for voltage and current in forward bias. This plot is exponential, not linear. But here what they are saying is, if you plot between any of these two parameters, one plot is going to be linear. They are saying. First of all, I versus Vs. I versus Vs, it is exponential. It is not like this. Now, just I am going to our current equation. Diode current I is equals to I naught into e power Vd by eta Vt. Now, these are the constants. For my easy understanding purpose, I am taking constants are, let us take it as 1. From this, we can write simply I is directly proportional to e power Vd. By taking natural log, so it is we can write it as a log I directly proportional to Vd. So directly proportionality, okay, to ln of I. So it is we can write it as 2.3 into log of I. But that anyway, that is a constant. Log I directly proportional to Vd. That means both are directly proportional. That means both are linear. So log I and V. Vd means here it is V. So I am taking V. Because in this problem they mentioned clearly it as V. Okay, so log I directly proportional to V in this sense both are linear to each other. Directly proportionality is linear to each other. So by drawing a plot between log I versus V, you get it as a linear one. It means if you draw a plot like this, log I versus V, that plot is going to be a linear one. Linear one. That is the meaning of this. Okay. So now log I versus V, this is the correct option. Correct option, this one. So is it clear? Next. Now I'm going to next problem. See this. In an ideal PN junction with ideality factor of 1, clearly they given, sir, ideality factor is 1, eta is 1, they given clearly, at T equals to 300 Kelvin. The magnitude of the reverse bias voltage required to reach 75% of its reverse saturation current is, sir, the magnitude of reverse bias voltage. What is the reverse bias voltage required to get the magnitude of bias voltage required to reach 75% of its reverse saturation current? So you have to reach the diode current is 75%. 75% of reverse saturation current I naught. Okay, now first I am going to representing the diode current equation. So our diode current equation ID is equals to, we know that I naught into e power Vd by eta Vt minus 1. Okay, eta Vt minus 1. Now From this I am writing Vd is equals to voltage across the diode, what we are applying, is equals to eta Vt into, taking I naught this side, just a little bit modification, Id by I naught plus 1 equals to e power Vd by eta Vt. Now Vd equals to eta Vt into ln of 1 plus Id by I naught. Now we are applying the condition what they given. Now your diode is under reverse bias. In reverse bias we can take Vd is Vr. Okay, therefore Vr equals to, Vr value is, you need to calculate Vr is eta Vt into ln of 1 plus, diode current should be 75% of I naught. And one more, when diode is forward bias, this is the direction of the current, Id. In reverse bias, this is the diode current, I naught. In reverse bias, the current Id and I naught both are opposite. So you can take Id is minus 75% of this current, 0.75 times of I naught divided by I naught. Now simplify this. So this is eta is 1. So and Vt is 26 milli, means 0.026 into ln of, it is both will cancel, I naught gets cancelled, 1 minus 0.75 is 0.25. Simplify this, ln of 0.25, ln of 0.25, it is a minus 1.38. So into 0.026, that is minus 0.036 volts you have to be applied. Okay, this much voltage you need to apply to reach, see, volts, it is 0.036 volts. Okay, that means it is a 36 millivolts you need to apply in reverse bias to get a diode current through the diode is 75% of its reverse saturation current. That means in plot, I am going to plot it. So only reverse bias we need. So this is the, so here it is a reverse current. This is the reverse current and this is the applied reverse voltage. Now the plot is, this is the plot for it, its plot. For detailed analysis purpose I am writing little bit more in detailed. This is the peak value, saturation value of I naught. This is the saturation value of I naught, this one. So to reach 75% of it, 75% of it means 100%, this is maximum value, somewhere here 75%, this much. To reach this much, to get this much current, you need to apply this much voltage. It is in a reverse direction, so negative voltage, that is 36 millivolts you need to apply. So minus. Okay, by applying that much voltage, you get 75% of maximum diode current in reverse bias, saturation current. That is the problem. Okay, sir. Yeah, next one. In the circuit shown below, the switch was connected to position 1 at t less than 0, and at t equals to 0 it is changed to position 2. Assume that the diode has 0 voltage drop and a storage time t, and storage time ts for 0 less than t less than or equals to ts. Vr is given by dash in volts. Okay, sir, see what they are saying is initially your switch is connected to position 1. Okay, and at t is equal to 0, switch is connected to position 2. Okay, and voltage drop across the diode is 0. Okay, and its storage time is ts for 0 less than t less than or equals to ts. Okay, what is the VR voltage? What is the voltage across this resistor? They given VR is minus 5 volts, plus 5 volts, 0 less than or equals to 5 volts, and minus 5 less than VR less than 0. Which option it is? Okay, before going to that, you should know what is storage time, because that is the new term we have. Okay. Yeah. Now, see, first you should know what is storage time. Then only you can understand this problem effectively and you can easily solve that problem. Okay. Now, before going to this, first I am going to representing the way of minority carrier distribution at junction in forward bias as well as reverse bias. Okay, see, now first I am taking the forward bias. In forward bias, how minority charge carriers are distributed in P region as well as my N region. Fine. So let us take this is for forward and this is for reverse. For better understanding, I am maintaining some distance between P region and N region, some separation I am maintaining, and here also I am maintaining some separation. This is for better understanding purpose. Okay, now this is P region and this is N region. Similarly, P region and N region. Minority carrier distribution here first I am going to. So in P region, let us the number of charge carriers are this much, number of electrons are there. Similarly in N region, this much number of holes are there. Here also similarly this much number of electrons are there and this much number of holes are there. Okay, for better understanding I am taking a little bit more this side. This is the case in reverse bias. This is the case in reverse bias. Okay, now already we discussed much about this one in previous class. In forward bias, P connected to positive, N connected to negative. Once P connected to positive, whatever the holes in P region, okay, they are drift from P region to N region. Once they entered into N region, holes entered into N region, they became minority charge carriers. Okay, here these are the holes. So once entered into holes entered into N region, they became minority charge carriers. Now let us this much number of holes are entered into this. This much number of holes are entered. Now they are going to be diffusing like this. During diffusion, their concentration is going to be decreasing. This is the whole movement in N region. Holes are minority charge carriers in N region. Similarly, from N region to P region, we are getting some electrons drift. Once electrons drift into the N region, drift from N region to P region, they diffuse like this, like this, like this. Okay, like this. They diffuse like this. So this is the movement of electrons. Okay, now the amount of charge carriers which are entered from P region to N region, holes entered from P region to N region, as well as electrons which are entered from N region to P region are called excess charge carriers. Excess charge carriers. Excess charge carriers. Excess or injected charge carriers. Excess or injected charge carriers. Okay. Now, I'm going back to reverse bias. In reverse bias, see, these are the electrons. Don't forget, these are the electrons. Okay. These are the electrons and these are the holes. In reverse bias, the situation is P connected to negative, N connected to positive. Listen carefully. Here, your electrons are like this. These are the electrons. Here, these are the holes. Let us assume. Now, see, this negative is going to repel this electron, and this negative, this electron repel this electron. These two electrons and this negative repel this third electron. Like that, all these electrons except this and this one negative is going to repel this electron. Similarly, this positive and this hole repel this. These two holes and this positive repel this hole. These three holes and this one repel this one. Like that, by moving towards the junction, repulsive force is more or increasing. By moving towards the junction, repulsive force is increasing. Due to that repulsive force, whatever the charge carriers present at the junction, they are cross the junction and they recombine with the electron and hole. Now these are going to be recombined with this. This is recombined with this. So there is a recombination, more recombination at junction. And by moving away from the junction, repulsive force is decreasing. That's why recombination is also decreasing. That's why some charge carrier concentration we get like this. Similarly here also like this. Now I am representing this one on another plot. Now let us take, this is the junction. This is a P region and N region. Under steady state electron concentration, under steady state hole concentration. Now by moving at the junction, by moving away from the junction, repulsive force is decreasing because of that concentration of holes, electrons are increasing by moving away from the junction. Similarly here also the same thing takes place like this. These are the holes. Okay, now this is the under steady state conditions. Your reverse biased junction should be like this. Under steady state condition, your forward biased PN junction should be like this. So it is the minority carrier distribution. in a junction under steady state condition. So these plots are very important, sir. Minority carrier distribution under steady state. So this is minority carrier distribution, carrier distribution minority carrier distribution at junction under steady state, under steady state. So whenever your carrier distribution is like this, then only you can set your PN junction diode is under forward bias. And whenever carrier distribution is like this, then only you can set your PN junction diode is under reverse bias. That is the meaning of this. Now what I am going to doing here is just I am going to be changing my junction diode from forward bias to reverse bias. That means initially your diode is connected in forward bias like this, it is in forward bias, it is in forward bias initially. When it is forward bias, the carrier distribution is like this, minority carrier distribution or excess charge carriers are present. Okay, now at a time t less than 0, this is the case. At time t equal to 0, what I done is just I bias this one in reverse bias. I changed the polarities of the battery. Now your diode is under reverse bias. Okay, when it is reverse bias, your carrier distribution at a junction should be like this. But the moment at which you change the terminals of the battery, at that moment, the distribution of the minority charge carriers is like this. Okay, now there are excess charge carriers present in this. Excess charge carriers are presented here. Okay, but there is no excess charge carriers here, and that too there is no charge carrier at all at the junction. So your excess charge carriers what you have during forward bias, first this excess charge carrier concentration should be equal to 0. Okay, for that it takes some time. Now see, first this carrier concentration has to be changed like this, change like this first. This is the steady state value in N region and P region. Let us take. So P region and N region. First, it need to change its shape. That excess minority carrier concentration should be 0. For this, it takes some time from this point to change its level. Excess carrier concentration make 0 here. For this process, it takes some time. The amount of time it takes for this is called TS, storage time. It is storage time. Okay, so for up to storage time, even though your diode is under reverse bias, up to storage time, that means up to storage time in the sense excess charge carriers are present at the junction. So up to storage time, even though diode is under reverse bias, the diode is on state. So therefore, up to storage time, even though diode is under reverse bias, it is in conduction. conduction. In this sense, on state. It is in on state. On state. Up to storage time, your diode is on state, even though it is in reverse bias. Okay. So that is the point here. Now, it is in on state. Now, after this, to change the steady state minority charge carrier from this location, this form to this form, it takes some time. That time is called transition time. That time is called transition time. This is called transition time. Transition time. So TR is transition time. So total time it is taking to switch from complete reverse bias, forward bias to complete steady state reverse bias. It taking sum of these two, storage time plus transition time. Now this is called reverse recovery time. TRR, reverse recovery time. This is the amount of time required for a PN junction diode to switch from forward bias, steady state forward bias to steady state reverse bias. So up to storage time, due to excess charge carriers present at the junction, our diode is under on state. Even though it is reverse bias connected in reverse bias, your diode is on state up to storage time. That is the important point. I think so all of you cleared this one, understand this one properly. Okay. So if you have any doubts, feel free to give your response in WhatsApp, in YouTube. Now see, now based on this knowledge, I am going to solving this problem. So far I know what is storage time. Now I am going to calculating this problem. See this problem. See, in this circuit shown below, the switch was connected to position 1. Okay, switch is connected to position 1. First it connected to position 1 for t less than 0. Okay, when it is connected to position 1, your diode is under forward bias. Under forward bias, it is ideal switch they mentioned. Okay, t is equal to 0, it is connected to position 2. At t equals to 0, it is connected to position 2. So at t equals to 0, it is switched to position 2. Okay, assume that the voltage drop across diode, that the diode has 0 voltage drop. When it is forward bias, the voltage drop across the diode is 0. That means it behaves like a short circuit. It behaves like a short circuit. That is the meaning of 0 voltage drop. Okay, and a storage time Ts. For 0 less than Ts, less than or equal to Ts. That means in a time 0 less than T, less than or equal to Ts. Just means just before Ts, in between 0 to storage time, what is the output voltage in that period? See, we know that just before we completed, up to storage time, even though diode is reverse bias, the diode is in on state. See, now at position 1 it is forward bias. Now it acts as a forward bias, means short circuited. At t equal to 0, it is switched from position 1 to position 2. Now your diode is connected to position 2. Okay, now position 2 in this sense, here it takes your diode into forward and here it connects your diode into reverse. When it is connected to reverse bias, at junction, your charge carrier distribution at junction is like this, under forward bias. So to set it as in reverse bias, it should change from this form to this form. For that it takes reverse recovery time. So up to storage time, diode is on state. So due to that, up to storage time, your diode is on state. So once a diode is on state, the voltage across VR is nothing but a voltage at this point. This is simply connected to negative terminal of 5 volts battery, and it is ground. Now the voltage between these 2 points is simply minus 5 volts. That's it. Minus 5 volts. So VR is minus 5 volts. Because up to storage time, diode is on. Diode is on state. But not in forward bias. This current is due to the stored charge carriers. Stored charge carriers what we have at junction. Okay. So this is the very important point, sir. Okay, you get this one in a switching characteristics of diode. You get this. Okay, next. So this is the concept involved in this. First, understand this concept thoroughly. Okay, then you can easily solve the problem. Based on this knowledge. Yeah. Now I'm moving to next problem. Just a minute. See, the current through an ideal PN diode at 300 Kelvin is 2 milliamperes when 0.1 volt forward bias is applied. Find the reverse saturation current. So they given diode current, what they given is 2 milliamps, and applied forward voltage VD is 0.1 volt. Okay, so temperature 300, that means you can take VT is 0.026 volts. Now what is the reverse saturation current I naught is how much? Okay, now I'm going to standard current equation. This is the equation. ID equals to I naught into e power VD by VT. Eta VT, okay, I'm taking eta is 1. Now we need I naught, therefore we can write I naught equal, okay, ID is I naught into e power VD by VT. Just simplify. They given ID 2 milli into 10 power minus 3 equals to I naught into e power VD 0.1 by 0.026. Now simplifying this, 0.1 divided by 0.026, that is 3.846. we need e power of it, e power x, that is 46.8. therefore I naught is 2 into 10 power minus 3 divided by 46.812, because its value is 46.812. now 2 divided by 46.812, it is 0.04272 into 10 power minus 3 amps. They given options in a nano and micro. Now I'm trying to change the options, change the units. Now I naught is 42.7 microamps, because it is 10 power minus 3, 10 power minus 3, 10 power minus 6 micro, 42.7 microamps. So this is the closest value, 43.7. Okay. Simple problem. Yeah, see this. Now the next problem is simply they given a circuit diagram to you. From this circuit diagram you have to show that e power q v1 by kt plus e power q v2 by kt equals to 2 if the diodes are identical and also made of germanium. Once both are made of germanium, you can take it as eta is 1, and e power q v1 by kt in the sense e power k v1 by kt by q, v1 by kt by q in this sense vt, e power v1 by vt plus e power v2 by kt has to be, you have to prove this is 2. Okay, so that is the data. Now first of all, here your diode is going to be up biased with supply voltage V. Okay, now with this supply, this diode V1 is under forward bias and this diode V2 is under reverse bias. V2 is under reverse bias. Okay, so it is clear from the circuit. V1 is diode D1 is, that is I am taking this is a D1 and this is the diode D2. D1 is forward bias and D2 is reverse bias. Okay, so once one is forward, other one is reverse. Okay, you can write the equations. Once it is forward bias, the diode current equation is ID1. Okay, and the diode current equation for this one is, let us I am taking in the same direction. It is a forward current, let us, okay, it is reverse current. This is the direction of the reverse current I0. Okay, in forward case, in case of forward, its current is like this, that is ID2. Now here I0 is equals to minus ID2. Okay, otherwise we'll go, don't confuse, I do one thing. Okay, now see this. This is the reverse current flowing in this direction. If your diode is in forward bias, okay, the current is flowing in this direction. Now that current and this current both are in opposite. Okay, so your diode forward current ID2, if I take it in this direction, let us take ID2. This one is opposite to this, so it became minus I0. Okay, because your diode is in reverse bias, that's why I am making this forward current equals to I0. Okay, forward current ID2 is minus I0. Just I am changing the direction, and my intention is to define reverse current, in terms of applied forward voltage, because here I want e power v2 by k vt, sorry, it is v2 by vt, not kt. So it is vt. Okay, I want to represent v2 by vt in terms of this, because of that I am taking here, and this is I0. And one more thing, whatever the ID1 you are representing, this ID1 and this I0 both are same because both are in series. Therefore ID1 is equals to I0. But I0 is nothing but you are representing I0 is minus ID2. Now just write the equations for both. Okay, ID1 is I naught 1 reverse saturation current of first one into e power Vd 1 voltage across this one is V1 by Vt minus 1 equals to Id2 minus Id2 value I naught to 2 into e power V2 by Vt minus 1. And one more, the diodes are identical. Diodes are identical. The meaning of this one is, whatever the reverse saturation current of first diode and the reverse saturation current of second diode, both are same. So therefore we know I naught 1 equals to I naught 2. Just I am going to cancel this. Okay, just cancel that. So these two gets cancelled. Therefore simplify this. Now it is e power V1 by Vt minus 1 equals to minus e power V2 by Vt minus into minus plus 1. Take this one this side and minus 1 this side. Therefore e power V1 by Vt plus e power V2 by Vt equals to, take this one this side, 1 plus 1 2. So that is what they want. Okay, this is what they are expecting. E power V1 by Vt plus e power V2 by Vt to equal to 2. Here they expanded that Vt, Kt by Q, that's it. So like that, by applying simple analysis, okay, you can easily calculate anything. Okay. Next. See, this is also similar type of problem. For the circuit shown below, calculate the voltage across each diode if the diodes are identical and also made up of germanium. They given 200 millivolts across that. Okay, so once they given 200 millivolts across that, and we know that this diode is let us taking it as 1 and taking it as 2. This problem is similar to previous one. Okay, and one more, this is a plus minus, let us take V1 and it is a plus minus V2. From this you can write 200 is nothing but apply KVL to this. 200 volts, 200 millivolts is equals to V1 minus V2. V1 minus V2. Okay. So you need to calculate voltage drop across this one and voltage drop across first one and voltage drop across second one. Both are series. So let us take, this is the forward current if I get ID1 from this, and this is the forward current if I get ID2 from this. Okay, but both are opposite direction, therefore ID1 equals to minus ID2. So ID1 equation I am going to be writing I naught 1 into e power, similar to previous case, sir, e power V1 by Vt minus 1 equals to I minus I naught 2 into e power V2 by Vt minus 1. Simply we get finally, because both are identical diodes, so I naught 1 equals to I naught 2, both will cancel. Therefore finally we get V1 by Vt plus e power V2 by Vt equals to 2 we get. Okay, now from this just I am going to writing the value of V1 equals to 200 means 0.2 plus V2, that is V1. Substitute that V1 value here. Just substitute the value. Therefore e power V1 is 0.2 plus V2 by Vt plus e power V2 by Vt equals to 2. Now we can write this e power 0.2 by Vt into e power V2 by Vt plus e power v2 by vt equals to 2. From this I am taking e power v2 by vt common, then it became e power 0.2 by vt value 0.026 plus 1 equals to 2. Okay, now just simplify that. So 0.2 divided by 0.026, it is 7.69. I want its e power of it. It is 2191.4. Okay, plus 1 this is, so e power v2 by vt equals to 2 by 2194, sorry, 2192.4. Simplify that. 2 divided by 2192.4, that is 9.12 into 10 power minus 4. 9.12 into 10 power minus 4. So that is the e power v2 by vt. Therefore v2 is vt into ln of 9.12 into 10 power minus 4. Just simplify this. So v2 is vt 0.026 into ln of 9.12. So ln of 9.12 is 2.21 plus ln of 10 power minus 4, that is minus 4 into 2.3. So it is so 4 into 2.3 minus 2.21 6.99 into 0.026, that is a minus 0.18 17 or 181 volts. That is the V2 voltage. Voltage drop across this one is negative. Why? Because your diode is in reverse bias and we need V1. Therefore V1 is 0.2 plus V2. So 0.2 plus V2 value minus 0.181. Okay, so minus 0.2, that is a 0.0182 volts. Here you observe one thing. In a forward biased PN junction diode, voltage drop across forward biased PN junction diode is low and voltage across reverse biased PN junction diode is high, magnitude point of view. Okay, because the amount of resistance offered by the junction when it is in forward bias, it is low, that's why low voltage drop across that, and the amount of resistance offered by this junction is high, because of that it is high resistance, that's why high voltage drop. Okay, now apply the same procedure to the remaining problems also here. Now I think so the same problem, but additionally what they are saying is repeat the above problem if a series resistance of 5 kilo ohms are connected with I naught is equal to 5 microamps. See, additionally 5 kilo ohms is connected with I naught. So there is a reverse saturation current they given, it is 5 microamps flowing through that, and you need to calculate the voltage across this. What is the voltage across this and what is the voltage across this? Okay, now here simply one thing, this 5 microamps is also flowing through this. Now the drop across this one is 5 into 5 kilo into micro, 25 milli, so that is 25 millivolts, that means 0.025 volts, 0.025 volts. Okay, and from these two, if I take this is plus 1 and this is 2, V2, we can write 200 milli means 0.2. 0.2 is equals to 0.2 equals to V1 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 minus V2 plus 0.025 plus 0.025. Okay, now V1 minus V2 0.2 minus 0.025, that is 0.175. 0.175 volts equals to V1 minus V2. Previous case V1 minus V2 is 0.2. Now this case it is 0.175. Just to follow the same procedure. Okay. So next one. Here also same thing. This is the current I. Here let us take the applied voltage is V. This is current I. Now let us assume this current is splitting. I1, it is I2, and voltage is V. So that means the voltage across this one is same voltage, and voltage across this one also the same voltage, opposite voltage. Yeah, it is positive, it is negative, it is V. That means it is reverse bias. Okay, but so once it is a reverse bias, it is I1. Let us, I am taking this is the I2, that is the reverse current I0. Okay, both the diodes are identical, they mentioned clearly. Now this current flowing through this one is I0, this current is the I1, because this diode is under forward bias, this diode is under reverse bias. Now this is the entering current I. Now we can write, just applying KCL at this node. According to KCL, the sum of entering currents equals to sum of leaving currents. Therefore entering current is I, leaving current is I1, forward current plus, sorry, another entering current I0 also is there. I0 is also entering. Okay, so this is I. Next one is, so from this I is equals to I1 minus I0, I1 minus I0, I1 minus I0. Okay, now I am writing the equation for I1. I1 is I0 1 into reverse saturation current of first one into e power V by eta Vt minus 1 minus I0. See, we can write I0 is nothing but a minus of ID2 or I2 if I take I2 this side. Okay, I am going to applying that. Plus minus into minus plus I2 we need, or we can write directly this equation is I1 plus I2. Now therefore I is equals to I0 1 into e power V by eta Vt minus 1 plus I2 is I0 2 into e power voltage across the diode is plus minus, this is okay, with respect to positive we need to represent, so minus V by eta Vt minus 1, eta Vt minus 1. But from this we can write I0 1 equals to I0 2 equals to, I am taking it as I0 because both are identical diodes. That's why I am representing I0 1 equals to I0 2 equals to I0. Just to substitute that. Now I am taking I0 1 equals to I0 2. Therefore we can take it as a common I0 into e power V by eta Vt minus 1. Okay. And Sorry sir, it is just a minute. I is I1 plus I2, but I2 is opposite direction. Sorry, little bit modification, sir. We done everything clearly, but small modification. See, this is I2. Now I equals to I1 plus I2. Fine. I equals to I1 plus I2. I1 plus I2. But whatever the I2 we have, that is minus I0. Okay. Compared to this current, it is opposite direction. That's why you have to take it is negative. Okay. Sorry. Diode position is now this is I2. Now I think so you are clear. No confusion. Forget about I0 and all this. Now it is clear. This is I1. Just during that color I confused about this diode. This is I1. This is I2. Now I is entering, I1 is leaving, I2 also entering. Therefore I plus I2 equals to I1. Therefore I2 is simple I1 minus I2. This is the I1 value minus I2 value. Just write minus I2 value. Now I am writing that values here. I1 minus I2. So it is minus I0 already I0 I taken common. Now it is minus e power v minus v by eta vt minus into minus plus 1. So these two gets cancelled. Therefore it is I0 into e power v by eta vt minus e power minus v by eta vt. This is the equation for I. So I am writing this one as I is equals to I0 into e power v by eta vt minus e power minus v by eta vt. This is. Now just I am dividing this with 2 and multiplying with 2. No doubt, no change. So e power x minus e power minus x by 2, that is sine h inverse of x. Okay, so it is 2 I0 into, it is sine h inverse of x, sine h inverse of, sine hx, not h inverse, sine hx, x value is v by eta vt, so that is the answer. 2I0 into sine h value, sine h v by eta vt. So this is the answer for that. Just check the options. 2I0 into sine h v by eta vt. So if you want in terms of voltage, you can change that one to inverse. Okay, so if you want voltage v value, you can take 2I0 this side, eta vt this side. Now eta vt into, see, now the voltage v is eta vt into sine h inverse I by 2I0. So you get this value. Okay, yeah. So this is the problem. Now we are moving to next one. So this is also the similar to that. Previously already we done this model problem. Instead of 5 volts, previous problem we have 0.2 volts. Yeah, see this. This is the problem. Following figure shows the spatial distribution of excess minority carrier hole concentration on the n side of two ideal p plus n diodes A and B. So this is the N region. In N region, hole distribution they given by this plot. Two diodes, both are identical. A and B diode maintain at room temperature. Assume low level injection condition prevails. The P diode, P side doping, N side doping, the cross sectional area and hole mobility are the same in both the diodes. Which of the following statements is not correct? So they given 4 statements. In these 4 statements you have to give which statement is wrong, which statement is right. You have to first identify. Okay. Now in N region clearly they are saying hole distribution. This is the hole distribution in N region. In N region this is the hole distribution. That too your hole is diffusing, and during diffusion recombination is taking place. Because of that it is decreasing exponentially. Already we studied in our diode current equation. So both the diode, see both for A diode and B diode both are diffusing. That's why both the junctions are in forward bias. So both the junctions are in forward bias. So this is the true statement, correct statement. It is correct statement. Now I am going to B. Diode A has higher applied bias. Yeah, because of that only amount of charge carriers injected from P region to N region is more, because it is high potential, high voltage applied. So in B diode, amount of charge injected from P region to N region is less. That means less applied forward voltage. So diode has a higher applied bias. Yes, it is correct statement. It is also correct statement. Diode A has higher current. Yes, because once high amount of charge carriers are injected from P region to N region, that means high charge carriers are crossing the junction, automatically we get the high current. This is also a true statement. Now diode has A has higher minority carrier whole lifetime. See, lifetime, we know the equation for lifetime is equals to square root of D into tau. Okay, lifetime is, sorry, whole lifetime. This is the diffusion length is directly proportional to D into tau. So D is constant for both electrons and holes. That if diffusion length is high, it means lifetime is high. Diffusion length is less, lifetime is less. See, diode A, within a short distance they are going to be completely recombined. That means diffusion length for A is less. Once diffusion length for A is less, okay, diffusion lifetime also less. So diode A has higher minority carrier lifetime. So minority carriers here are holes. Okay, now it has holes in A diode has less lifetime. This is the correct statement, but they given diode A has higher minority carrier lifetime. This is the wrong statement. This is the wrong statement. So you need to identify the not correct statement. What is the not correct statement? Wrong statement you need to identify. This is the wrong statement. Okay, so this is the wonderful question. So my dear students, just once you are thorough with concepts, whatever the problem it is, you can easily solve that problem. Okay, now thank you. Thanks for spending your valuable time with us. Don't forget to use my code during subscription VROW10, and please hit the bell icon for getting the notifications. Don't forget to subscribe, and please join our Telegram group for latest updates on our upcoming videos. And please give your valuable comments on YouTube. That is the strength to us, and we are welcoming you all once again to Unacademy, the India's largest online learning platform. Thank you. Thanks for spending your valuable time with us. Thank you.